This is my introduction to the passive solar geothermal walipini. Now, I guess technically a walipini usually, or in all cases, implements passive solar, but I take some extra measures and it's geothermal. It so it will take energy, it will take electricity, but not much. Geothermal is a pretty efficient heating method. So I guess I'll go through the pictures I have to represent, what this would be like. So you have the length of this. Now this is just an idea for one I'd make. So this is not any universal measure right here. And of course I don't have a lot of the geothermal aspect worked out either. But I'll just go over what this is. So what you see is a 96-foot, greenhouse. Of course you have this right here would be a window facing south. You wouldn't want it facing north in the northern hemisphere because the sun wouldn't be shining in. And then this right here, which you cannot see in this picture, would be the back of it, which would have some form of, insulation, you could say. Well insulated. And I'll show you what I mean by that in a sec. But about 4 feet of it, about 4 feet deep, all the way across, this will be under the ground. So, that's part of the insulation or measures of insulation. And you can look up a walipini. You typically find that they are buried like that. And that's part of the preservation process. I wrote some of the measures on here. You can see 10 feet, which is the length from this to this, and then 8.08. That's about the measure from this to this right here. And I guess it doesn't give much more than that. So the glass will end up having the lowest R value, and that means it's got the least insulative property. It'll leak heat the easiest, but of course, it's also something we need to heat it. I mean, you have, and also the plants within the greenhouse will need light. I mean, there's many reasons it's necessary, and finding a glass with a higher R value will typically lower the amount of light that comes in and have negative effects. So you gotta weigh the good with the bad on that. So the thermal mass will be on the back and on the ground. It'll be, concrete, soil, water. I'll have like a tank right here, a large tank, to collect rainwater that flows off of this to water the plants inside, but also act as a thermal insulator. And of course, water holds a lot of heat. What's that called? Joules? I don't really remember. But yeah, water holds a lot of heat, so it also has great insulative property. It's a good thermal mass. And then, yeah, I guess, should I go on to the next one? So, I guess I'll just talk about the purpose of it. The purpose would be the purpose of the passive solar is to make it more efficient. Of course, that's the purpose of passive solar in anything. It's like free heat from the sun. So, yeah, the heat's expending the energy. You don't have to do any work for it, and you just take advantage of that. The bulk of the system would lie about the bulk of the geothermal system, sorry. The bulk of the geothermal system will lie about 4 feet below this, so 8 feet below grade, which is ground level. And yeah, that would be a digging process. That would take some money. But let me think. Some of the system intake would run. Oh, so I guess I'll go over the intake of the geothermal system, which I would probably have it run across the top of the geothermal greenhouse. The intake, I think I said that. It would intake, go in, go under the ground, do its thing, and then the output would be somewhere right here in the front of the system, so that the heat that comes out will rise, or cool air will just fill the ground. So I think that would be the best for utilizing the geothermal. And then that's it. Now I will go on to the next one finally. So this just shows the angles. Most of this, I can tell you, this right here, this here, and this here are sort of the base measurements. I don't know why I put that 3 on the end of that, but oh, okay, I guess I was just doing 4 significant figures. That's kind of useless, but it's fine. Yeah, so you have these right here were my starting measurements. The degree angles all were. And then this right here I extrapolated by using the law of sines and whatnot. And then same with this. And I'll go on to the math in a bit, but I just wanted to say this, yeah, the next one I have is more specific and better drawn, I guess. Not that, you'll understand when you see it. This right here is the soil that I was talking about. So you'll have a great insulative property right here when you have the soil either built up or you built it into the side of a hill. In my case, or the case I was thinking, it'd probably just be built up. But yeah, you can see this is about 4 feet under the ground, 4 feet below grade. And then, yeah, should be excellent for insulation. This is the more specific one I talked about because that last one's not very good. I designed it many, many months ago. And yeah, the measurements I showed you were all the same, but I put here I guess it's oh yeah, and this. I put those there and I calculated the math for you. Of course, the length of the system's 96 feet, and I showed you that earlier. And this is only in my case, once again. This isn't a general rule. This is just the idea I'd have to make a greenhouse like this. All right. So finding the square footage of the system, so that would be the width of the system times the length. No 3-dimension involved. This is just the ground square footage, and that's about 1,152 square feet. And yeah, that'd be like enough room for, if we're all put together, it'd be enough room for a house, I think, a small house. I'm trying to think about square footage of mine. And then when it comes to things like calculating the degree angles, of course, I split this right here at a 90-degree angle. So now this is 90 degrees. If the whole angle is 150, then 150 minus 90 is 60. So this is 60 degrees. If we know this is 90, then this is 30. Once again, this is 90. So 90 plus 30 is 120. And if the whole angle is 150 degrees, then this is 30. So this is 90. And we get that this is 60. Once again, it's just two 30, 60, 90 degree triangles, which that's pretty nice to do math with. It's pretty, what am I trying to say? It's easy math right there. And I don't even know if I'd use the law of sines. I think I forgot the quick way of doing it. But yeah, I just showed you how I did more degree angles, and then I used the law of sines to find, oh yeah, I didn't have to do that. I knew that this would be, or no, this right here would have been half of this, and this is like, I don't know, something with a square root of something. I didn't have to do all that math, but it's fine. It's quite fine. Because I got all the numbers I needed, right? That's all that matters. So after doing that, I got that, of course, the whole length of this is 12. This is 5 feet. If it's 12 minus 5, you get this is 7. So this right here is 7 feet. And then from there, I mean, I had all the degree angles, or the degree measures, so I could calculate the length of this and this. and I know the length of this. It's 8.66. This right here is 4.04. Yeah, that's this right here. So then you add another 4 feet to that, and you get the height of the back of the system, which is about 16.7 feet. So it's almost 17 feet, and I think the average room in a house standard is 8 feet. So just imagine possibly your own bedroom times 2 plus a little more. And yeah, that's good enough for the trees that I'd have put in it. And this is actually made for tropical fruits right here. You know, I'd have ways of maintaining a good humidity level to prevent mold, but also be good for the trees. And 17 feet is certainly enough. I won't be growing any trees that grow to massive heights. So what is all this? This is the square footage of each of these pieces. So this is a bit of a mess right here. So this right here correlates to this. So 4.04 times 7 divided by 2 get you the square footage of this, and so on. And through that, I got that the face of this is 144.42 square feet. And then that, the square footage of the face, times the length of the system will get you the cubic footage. So the air that you'll have to heat and cool, or the air that will serve as an insulative property itself. So of course, a smaller system is probably going to be more susceptible to swings in temperature, which is common sense. Do I go on to the next one? I guess I suppose I do. This just shows some, oh, this is also an old graphic I made. This is pretty bad now. And I have reasons for all of this, because you see this stupid number right here, and this questionable number right here, and you're thinking, what is the point of that? Well, I guess I sort of intended for from this point to this point to be about 30 feet, and from the start of the slope, so you have like 4 to 5 feet right here that is level with the greenhouse. Then it starts to slope down, and this of course isn't the case that you have to build it up, but I made it it goes to the right 2 before it goes down 1. So what would that be? A slope of 0.5? I don't know. Sounds right, because this right here is half the length of this, and that's how I got the degree measures also, which this is probably pretty bad, but it's fine. And this is different right here. So what this is showing is just an idea. This isn't really exactly what you'd do. If you built the whole system and all that's said and done, then you could find a tree, and of course you'd probably have to trim it and be sure it's not a tree that grows really wide. But you could certainly use a tree so that probably a deciduous tree. You wouldn't want that one that's evergreen, because there's the chance that it shades your greenhouse during the winter, which you certainly don't want any shade in the greenhouse during the winter. But you gotta think, this would be representing about midday. Evening and morning, the sun would be hitting the back of the greenhouse just fine, but during midday, when the angle of the sun is very high, the sun may get caught by some of this supposed tree, or this possible tree that you might place, and all of this, I'm trying to represent that, all of this might be shaded, which would be helpful during midsummer. Of course, during the winter, even though this is going to be a deciduous tree and its leaves are all going to be everywhere and you're going to have to go rake them up, even though this is a deciduous tree and the sun would be able to go through that during the winter anyway, also the angle of the sun is lower, so even the branches won't be a problem. And that's kind of what I'm trying to represent. This is also a good idea to some degree. You wouldn't want it to shade your plants because your plants need light, but to shade the back of it where the bulk of the insulation is, I guess you could say, is one of the most important things you could probably do around midsummer. And of course the floor is going to retain some heat, but you'll have trees to also absorb it. And this is about it. I mean, I could think up more ideas. This is one of the most interesting things to me. The ability to the ability to save energy, one, and also the ability to possibly grow fruit, tropical fruit, in a greenhouse. Maybe I should have shown a graphic of the trees I'd plan on getting. I can do that in a bit. So that's all I have to say on this. I I hope the right person sees this. If somebody has any ideas or could contribute or would possibly like to set up a plan for constructing such a thing. It's pretty nice, and you can just look up walipini or geothermal greenhouse on YouTube, or well, if you look up what I titled, I'm going to title this video, you probably won't get much. Passive solar geothermal walipini. That's just me being a bit dramatic about the topic, I guess. But oh man, I'd love to be able to construct something like this. It's kind of a dream of mine, but it's fine. Life will go on. Thank you for watching. Bye for now.